Okay, today's topic is sequential circuit. We already covered the combinational circuit. Next topic is the sequential circuit. Now, the sequential circuit it consists of combinational circuit with a storage element. So, if you represent a sequential circuit as a block diagram, we can represent the sequential circuit as a combination of a combinational circuit and a memory element. So here you can see that the output is stored with the help of a memory element, and the output of your sequential circuit depends on the input as well as the present state. That means the sequential circuit output will be a function of both the input and the present state. Before going to the sequential circuit and its details, first we can just go through the comparison of sequential circuit and combinational circuit. It's already given in the slide. We can check the points one by one. So here you can see that in combinational circuit, the output variables at all time depends on the combination of the input variable. But in sequential circuit, the output variable depends not only on the present input variable, they also depends on the past history of these input variables. That means it depends on the previous output also. So that is one of the major difference between the sequential and the combinational circuits. Now we know that for combination circuit there is no memory is present, and whereas for sequential circuit we need a memory, because the sequential circuit output depends on the present input as well as the present output. So we need that information. So for finding out the next state, so we need a memory. Now combinational circuits are faster obviously than the sequential circuit, and if you check the design, you can see that the combinational circuit design is easier than the sequential circuit. So one example is given. Parallel adder is a combinational circuit, and for sequential circuit, serial adder is an example for the sequential circuit. Now the sequential circuits are classified based on the time at which the storage element observe their input and it changes their state. Based on this, it is classified as asynchronous and synchronous. So we will get into this later. What are the different types and what are the example for these circuits, and what is the difference between the comparison between the synchronous and asynchronous, that we will discuss later. Before that, we can just discuss the basic elements that is used in a sequential circuit. Now, flip-flop is an important, it is the basic memory element for a digital circuit. So the flip-flop is designed by assembling a different logic gates. As we know that the single logic gate does not have the capacity to store the data. So we will combine different logic gates in such a way that it can store a digital information. So flip-flop is such a circuit. Now there are different types of flip-flop with different characteristics for different applications. Now flip-flop is the basic building blocks for the most of the sequential circuits. Now if you check, you can see that for a flip-flop, we can store 1 bit of memory, and there are 2 outputs for the flip-flop. Generally it is marked as Q and Q bar. either q and q bar both can be used as an output. Now if you take q and q bar, whatever be the output present at the q, its complementary will be available at the q bar. That means the output of the flip-flop is complementary in nature. Now if the value of q is high, we will usually say your flip-flop is set, and if the q is 0, usually we will say your flip-flop is reset. Okay, it can store 1 bit of memory, and it is sometimes it is also known as a bistable multivibrator. We know the peculiarity of the bistable multivibrator. It has two stable states. So similarly, flip-flop also has two states. It can be either 0 or 1. Now if you want to change the output of the flip-flop, we have to change the value of the input, and we have to give a trigger signal for the change. Now by just simply changing the input, the output of your flip-flop does not change. You have to give a trigger signal to change the output of your flip-flop. As I already mentioned, there are different types of flip-flops with different characteristics for different applications. Now we can go through the different types. The first flip-flops is SR flip-flop. It is also known as the set reset. SR means a set reset flip-flop. It has two inputs, S and R, two outputs, Q and Q bar. Now if you take the truth table of an SR flip-flop, here truth table, it shows the S input, R input, and Qn plus 1. Qn plus 1 means the next state. This means next state of your flip-flop. So when R is equal to 0 and S is equal to 0, your next state is Qn. Qn means that is the previous state output. So when both inputs are 0, 0, the present output will be the same as the previous output. There is no change. Now if R is equal to 0 and S is equal to 1, your Q will be 1. So your flip-flop is said to be set. Now if R is equal to 1 and S is equal to 0, your output, that is Qn plus 1, will be 0. That means your flip-flop is said to be reset. Now if both R and S both are equal to 1, in SR flip-flop, this is an invalid state or invalid input combination. So usually this combination will not occur. If this combination occurs, you cannot predict the output, or you will get an invalid output. So we will see how these inputs are changing by considering the internal circuitry of SR flip-flops. So in the slide you can see the logic diagram of an SR flip-flop using NOR gates. Here this one shows the symbol that is used to represent the SR flip-flop. So here you can see the inputs S and R. These are the outputs Q and Q bar. This is the enable pin where we will apply the trigger signal for your SR flip-flop. Now this is the logic circuit using NOR gate. Here these are the three inputs, R, S, and enable, and the Q and Q bar. These are the outputs of your SR flip-flop. So here we will apply your clock signal. Now we can check the cases, that is the combination of the inputs and what are the output you will get. So first we can take the combination as R is equal to 0 and S is equal to 0. So this is the case, R is equal to 0 and S is equal to 0. So here you can assume initially your output is equal to 1 and 0. So this is the previous state output. Now when you give R is equal to 0 and S is equal to 0, here you can see that when there is no enable signal or the clock is not applied, this will be 0. So when this one is 0, when the enable pin is 0, this is an AND gate. AND gate output will be always 0 when one of the input is 0. So these two AND gate output will be 0 when your clock signal is 0, irrespective of the signal you apply here. Whether 0 or 1, the output will be 0. When these two are zeros, what you will get here, it is 0. Here I can see that it is 0, right? So here it is 0. So 0 0, when the input of a NOR gate is 0 0, the output will be 0 plus 0, its complement, that is 1. So this 1 will be fed back here. So this 1 will be fed back here. So here 1, it is 0. 1 plus 0, it is 1, and its complement, that is equal to 0. So when you give 1 and 0 as the input of an OR gate, you will get at the output as 0. So again this 0 is fed back to this NOR gate. Again this will be 1. So that means that is a stable state. So when En, that is the clock signal, is 0, the output will not have any change. Whatever be the input combination you apply, there will not be any change appear at the output. So again we can consider this Q is equal to 1 and Q bar equal to 0. Now we are making this enable pin as 1. Now R is equal to 0, S is equal to 0. Now here for this AND gate 1, we are applying 0 and 1 as the input. So the output of this AND gate will be 0. For AND gate 2, here it is 1, here it is 0. So again the AND gate output will be 0. So one of the input of this NOR gate is 0, one of the input of this NOR gate is again 0. Now from here 0 is fed back, so this is 0, so 0 plus 0. If you are giving the input as a 0 0 for a NOR gate, the output will be 1. Now this 1 is fed back to this NOR gate, that is NOR gate 2. So this will be 1, 1 plus 0, it is again 0. 0, 1 plus 0, that is applied to a NOR gate, so the output will be 0. So that means when you apply 0 0, whatever be the previous output, that will be the next state also. That is, previous state will remain as such. That means there is no change for the output. Okay, now we can take the next state. Next state means we can consider R is equal to 0 and S equal to 1. We can take R equal to 0 and S equal to 1. So we are making R equal to 0 and S equal to 1. So if you want to change the output of a flip-flop, you have to apply the clock signal. So you have to make E and S equal to 1. Now initially you can assume your Q output is 0 and Q bar output is 1. So this is the previous state. Now when you apply the input as 0 0, sorry 0 1, this is the AND gate 1, you can consider this is AND gate 2, this is the NOR gate 1 and this is the NOR gate 2. Now if you check the AND gate 1, you can see that one of the input is 0 and the second input is 1. When the input of AND gate, one of the input of AND gate becomes 0, the output will be 0. Now if you check the second AND gate, both input, that is the AND gate 2, both inputs are 1. So the output will be 1. Now we can check the NOR gate 1. So for one of the input of the NOR gate 1 is 0 the second input, that is Q bar, is coming here. Now the Q bar value is 1, so it is 1. Now 0 and 1 are the input of the NOR gate 1. Similarly, for the NOR gate 2, one of the input is 1, the second input is Q is equal to 0, so this will be 0. Now if you take the NOR gate 1, the inputs are 0 and 1. When 0 and 1 are given to a NOR gate, you will get 0 as the output. So this is 0. Now this 0 is fed back, that is Q is equal to 0. This 0 is fed back to the input of second NOR gate. Now the second NOR gate has the inputs 0 and 1. So again 0 plus 1, the output of NOR gate will be 0. So this NOR gate output will become 0. Now this 0 is fed back to the input of the first NOR gate. So this is 0. The NOR gate input is 0. Now if you take the NOR gate 1, both inputs are 0. So when both inputs are 0, the output of NOR gate is 1. So the output of this NOR gate 1 will become 1. Now the value of Q is 1. So this 1 will be fed back to the input of NOR gate 2. Now the NOR gate 2 inputs are 1 and 1. So when 1 and 1 are the inputs of a NOR gate, the output will be 0. That means NOR gate 2 output will be 0. That will be same as the previous one. So this is the stable state. Now you can see that when R equal to 0, S equal to 1, Q will become equal to 1 and QR will become equal to 0. So your flip-flop is said to be set. So these are the conditions for the inputs 0 and 1. Now we can check the next state, that is when R is equal to 1 and S equal to 0. This is 1 and this is 0. Again, you have to make the clock signal as 1 to have the change in the output. Now we can assume your Q value is equal to 1. Initially, before giving the clock signal, the Q value is 1, so Q bar will be 0. Again, we can consider this as the first AND gate, second, this is the first NOR gate, and this is the second NOR gate. Now, for the first AND gate, both inputs are 1, so the AND gate output will be 1. For the second AND gate, one of the input is 0, so the output will be 0. And for the first NOR gate, the inputs are, one of the input is 1, that is coming from here. The second one, that is coming from Q bar, it is equal to 0. And for the second NOR gate, one of this input is 0, this input is 1, because this is coming from here. Now take the first NOR gate, that is NOR gate 1. So the inputs are 1 and 0. When 1 and 0 are the inputs of a NOR gate, the output will be 0. So this output will change from 1 to 0. Now this 0 is fed back as the input of second NOR gate. Now the second NOR gate has the input 0 and 0. So 0 plus 0 as the input of NOR gate, your output will be 1. So the output of your NOR gate 2 will be 1. Now this 1 is getting fed back to the input terminals of the NOR gate 1. Now for NOR gate 1, we have the input as 1 and 1. So the again output is 0. So your NOR gate 1 output will be 0. That means this is a stable state. So this cycle continues, but the output will not have any change. That means that is a stable state. So when R is equal to 1 and S is equal to 0, the stable state is Q is equal to 0 and Q bar is equal to 1. That means your output is, or your flip-flop output is said to be reset. Okay, now we can take the next combination possible, that is R is equal to 1 and S equal to 1. We know that for SR flip-flop this is an invalid set of input combination. Now we can check what happens when you give S equal to 1 and R equal to 1 for a SR flip-flop. So we can assume initially Q is equal to 1 and Q bar equal to 0. This is the current state, that is before giving the clock signal. Now we are making R equal to 1 and S is equal to 1. So in order to work the flip-flop, you have to make your trigger signal is equal to 1. Now if you check the AND gate 1, you can see that both inputs are 1 for the AND gate, so the output of AND gate 1 will be 1. Similarly, for the second AND gate, both inputs are 1, so that output also will be 1. That means both AND gate 1 and 2 as the output 1. So if you check the NOR gate 1 and 2, one of the input of NOR gate 1 is 1 and one of the input of NOR gate 2 is also 1. Now we assumed that Q is equal to 1 and Q bar equal to 0. So this Q bar is getting fed back as the second input of NOR gate 1. So this is 0. So since one of the input is 1 and the second input is 0, when you give that to a NOR gate at the output, you will get 0. So your Q will become 0. Your Q will change to 0. Now this Q is getting fed back as the input of your NOR gate 2. So if you take the NOR gate 2, you have one of the input is 1 and the second input is 0. So 1 plus 0 you will get as 0. So the second output will also be 0. Now again this 0 get fed back to the NOR gate 1. Again the NOR gate output, NOR gate 1 output will be 0. So this will be the state that you will get at the output. That means Q is equal to 0 and Q bar equal to 0. This is an invalid state because we know that Q and Q bar both are complementary in nature. So if Q is equal to 0, you must get the Q bar as the 1. Since we are getting both as 0, that is an invalid state. So that will be the output when you give S equal to 1 and R is equal to 1 as the input of a SR flip-flop. Okay, we already discussed the SR flip-flop using NOR gate. Now in the slide you can see the SR flip-flop using the NAND gate. Now for the NAND gate SR flip-flop also we have the same combinations of the inputs. Now we can check one of the input combination and what will be the output. So we can say S is equal to 1 and R equal to 0. Suppose if you are taking this as the input combination, that is S equal to 1 and R equal to 0. Initially we can assume this is equal to 0 and this is equal to 1. That is Q is equal to 0, Q bar is equal to 1. Now in order to work the flip-flop, you have to give the trigger signal. So you have to make En is equal to 1. Now we can mark it as 1, 2, 3 and 4. For the NAND gate 1, the inputs are 1 and 1. So when both inputs are 1, the output will be 0 for that NAND gate. So this will be 0. Now for the second NAND gate, the inputs are 1 and 0. So when 1 and 0 is the input of a NAND gate, the output will be 1. So this output will be 1. Now if you take the NAND gate 3, one of the input is 0, second input is that is Q bar. So Q bar is 1, so Q bar is 1, so 0 and 1, so 0 dot 1, so it will be 1. So your Q will become 1. Now this one get fed back as the input of the NAND gate 4. So now the NAND gate 4 has the input 1 and 1. So when you give 1 and 1 as the input of a NAND gate, the output will be 0. So your output Q bar will become 0. This 0 get fed back as the input of your NAND gate 3. Now the NAND gate 3 has input 0 and 0. When the input of an AND gate is 0 and 0, the output will be 1. So the output will again 1. This 1 get fed back, and then again out of NOR gate 4 will become 0. That means that is the stable state. So when you give S equal to 1 and R equal to 0, you will get Q is equal to 1 and Q bar equal to 0 as the stable state. So we already discussed the different states of SR flip-flops, and we discussed that with the help of the internal diagram of the SR flip-flop. Now in this slide it is shown as the timing diagram of the SR flip-flop. That means what happens when the different state occurs, that is shown as the diagram. How here you can see that the first line shows the combination of the input, and the second one shows the R signal. This is a signal that we apply to the S signal, and the second one is the signal applied to the R term, input, and this is the clock signal we apply, and this is the signal that we will get at the output. Now we can see that the clock signal here, when the first clock signal, that is when the clock signal reaches A, initially it is 0, so when it reaches A it becomes 1. So when the clock signal is becoming 1, we can see that R is equal to 0 and S equal to 0. So when the clock signal become 1, here the R is 0 and S is 0. We know that the combination of S equal to 0, R is equal to 0, when it occurs, the output does not have any change. That means initially it is 0. So when the clock signal comes also, it remains as 0 because the input combinations are 0. Now at the instant of B, the clock becomes 0. Now here you can see that when clock is 0, here the R remains as 0, but S is changed to 1. But here you can see that the output does not have any change, because even though your input R is 0 and S equal to 1, 0, 1, but your clock signal is 0. So when the clock signal is 0 means whatever be the input combination, the output will not change. So the output remains as 0. Now when the clock signal again becomes 1 at the instant of C, here the input is 0 and S input is 1. So when S equal to 1 and R equal to 0, we know that the combination occurs 0, 1 means the output will become 1. So here the clock signal is 1 and the input combinations are 0 and 1. That is why your output is changed from 0 to 1, because the input combinations are 0 and 1. The S is equal to 1, R equal to 0, and there is a clock signal, so the output will change. Now at the instant D, again your input is your clock signal is becoming 0. So here you can see that S is becoming 0 at this instant and R is becoming 1, but your output is just not changing at this instant because your clock signal is 0. So when for changing the state of a flip-flop, it is necessary to apply the clock signal. When clock signal is 0, whatever be the input combination, the output will not change. Now here you can see that again at the instant of E, your clock is becoming 1. At that instant, you can see that R is equal to 1, S is equal to 0. When R is equal to 1 and S is equal to 0, your output get reset. Here Q output get reset. So this continues. This cycle continues. That means whenever the input changes, you have to apply the clock signal, then only your output will change. If the clock signal is 0, means your output will not change whatever be the input combinations.